Okay, good afternoon, all the participants. Now we will start again the second session from Professor Masashi Chiba. The topic will be about the dark matter controversy in the Milky Way and the local groups. And yeah, we invite you for all questions related to this lecture. Put in the chat room, and I will call all the student for the question for giving these questions, and if the time is up, and we will collect all the questions and give to Professor Chiba. Okay, please, Professor Chiba.
Okay, thank you. Thank you. Yeah. Okay. So I have to show the. Can you see this screen?
Yes.
Yes. Okay.
See, yes.
Okay. Let me start. Okay. Thank you very much for joining, and thank you very much for giving me an opportunity to give a lecture for you. So this is the second part of my lecture, and first part. Yeah, in the morning, the Indonesian time. The lecture one is on basically introductory explanation for evidence of dark matter in the Milky Way and several issues in light of the standard dark matter model. So in this lecture too, I'd like to show some detail, and it's somewhat advanced, and it's basically the showing our recent result. So might be a bit complicated, but I'd like to make it. I'd like to try to explain in how to say the word which you can understand. So okay, let me start. Okay, so there are several issues in the dark matter model and observation. There's tension. So one of them is the missing satellite problem and core cusp problem. And here I'd like to show some of our recent work which tried to solve this paradox. And lastly, I'd like to show future prospects. So title is Progress to Solve Dark Matter Controversy in the Milky Way. So there are several small-scale issues in comparison of lambda CDM theory. Small scale means in the scale of galaxies and or satellite galaxies, say the length below 1 megaparsec. Beyond 1 megaparsec, lambda CDM theory is quite successful to explain and reproduce the large-scale structure of the universe. But there are several tensions below 1 megaparsec. This is small-scale issues. First one is missing satellite problem. There's overabundance of dark matter subhalos in simulation in comparison with only, say, 50 Milky Way satellites discovered so far. And I will show you in detail later. And there's a core cusp or too big to fail problems related to inner density profile or density distribution of each small subhalos within the host halo. And density profile is Cuspy in the lambda CDM, but there are some core dark matter satellites, as I show later. And theory predicts two concentrated massive subhalos in comparison with observed density distribution dark matter associated with satellites. And there are other issues. So there are several solutions to understand this tension. One is to adopt alternative dark matter models, such as warm dark matter model, self-interacting dark matter, nowadays fuzzy dark matter model, and a lot actually. So yeah, so due to these unsolved problems, there are now a lot of dark matter candidates proposed. Or there are some baryonic effects on the distribution of dark matter. This is okay, it's possible. And another one is still observational data is limited, especially many satellites are yet undetected, and also the observation data is not enough to set limits on the core cusp issues. So there are still some uncertainties or large uncertainties in the observational side. So, and in this issue, the dwarf spiral galaxies in the local group provide clues to these issues. Okay, why? Dwarf spiral galaxies are satellite galaxies in the Milky Way. Okay, so let me move on to the first topic, missing satellite problem. As already introduced in lecture 1, the numerical simulation based on dark matter theory predict hundreds of subhalos, like here. This is a distribution of dark matter particles in the Milky Way mass halo. Say video radius is say 250 kiloparsec or something. And there are a lot of small halos. This is so-called subhalos. And mass of each halo is from 10 to the 6 to 10 to the 9 solar mass. But on the other hand, Milky Way satellites, so far, only if, well, until a few years ago, there only 20 or 25 satellites are known. So, and after that, there are several surveys made, and as I show later. So, but still only 50 satellites are known. So there's a mismatch between this number of subhalos and the number of the luminous satellites. Okay. So this is a bit difficult, advanced, and complicated, probably a difficult part for many of the students here. But let me explain. Let me try to explain. This shows the power spectrum for dark matter, and the lower panel shows the mean density perturbation in the y-axis as a function of the scale concerned. It's in terms of wave number, or here is mass. And core dark matter theory is a power spectrum can be drawn like here, like this. So core dark matter theory has a lot of power in the small scale, or largest. The power is strongest in the small scale. So in the core dark matter theory, small scale collapse developed first from due to self-gravity, and larger scale formed later. So this power provides a lot of subhalos within the host dark matter halo. But to suppress the number of such subhalos, if one adopts a so-called warm dark matter is the compared to cold dark matter, the mass of each particle is of keV. Here the 1 keV, 3 keV, 10 keV. So if we adopt such a light dark matter particle, then the power is suppressed. And at what scale? The scale of 10 to the 6 to 10 to the 10 solar mass. And this is indeed a mass scale for dwarf spheroidal galaxies. Okay, it's a zoom in version. And you see a cold dark matter theory, power is larger for smaller mass scale. But if we adopt the warm dark matter, this power is suppressed so that finally the number of the small dark matter halos from this spectrum is reduced compared to cold dark matter theory. So actually, simulation show like this. This is result of warm dark matter in the Milky Way mass scale. Number of the subhalos is suppressed. So here show the number of the satellites as a function of the maximum circular velocity. Okay, this is instead of the mass here, the maximum circular velocity is adopted as an indicator of mass. So this is a cumulative number of the satellites. And warm dark matter theory, the number of satellites reduced, say like 120, 50 or something. So it's comparable to currently known number of the number of the currently known satellite galaxies. But CDM is, and this is the self-interacting dark matter theory predicts more, yeah, about a few hundred. So as I said, this dark halos on scale of dwarf galaxies are most important keys for this issue. So again, what are the dwarf spheroidal galaxies? It's in short, DSPHs. These are the dominant satellites in the Milky Way and also the Andromeda Galaxy in the local group. These galaxies have no gas and diffuse stellar distribution, and so it is a faint stellar system. And here shows some example of the dwarf spheroidal galaxies: Sculptor, Carina, Phoenix, Leo2, Leo1, so diffuse. But as I said, these galaxies are dark matter dominated. Mass to luminosity ratio is 10 to a few thousands or more. So these dwarf spheroidal galaxies are now regarded as an ideal site for the study of dark matter or nature of dark matter. Okay, so still many dwarf galaxies might be undetected so far. So based on this motivation, we are trying to search for new satellites using Subaru telescope we have. This is a Subaru telescope in the Hawaii Island. And in a prime focus, we have now a so-called HSC hyper-prime count. It's a very big digital camera attached in the prime focus. As you see, this size is compared with the typical size of the Japanese woman, and Japanese woman is small, so like this. And it has a wide field of view, so it's very important to look for new satellites. And this camera has several features. So okay, so armed with this camera and Subaru, we are now working on the systematic search for new dwarf satellites in the Milky Way. So here the some status of the search for those satellites. Here shows the V-band absolute magnitude of the satellites, and the y-axis is basically distance from the sun, or from the galaxy center. Sorry. Yeah, it's correctly from the distance from the sun, but the difference is between the distance from the sun compared with the distance from the galaxy center is not, it's small. So okay, anyway, sorry. It's y-axis is the distance from the sun, and as you see the non-Joe satellites distributed here in the right side, and these are the satellites known after strong SDSS survey, and this line shows the SDSS magnitude limit. Say SDSS is okay 20 with R band 21 to 22. So this is the magnitude limit. So with SDSS magnitude limit, as you see, still a lot of faint satellites at large distance from the sun are undetected or unexplored. So still, as I said, until a few years ago, after SDSS, just after SDSS survey over, only 20 or 25 satellites are known. This is due to this magnitude limit. But with HSC, the camera in Subaru, then we can explore this region, and we like to discover new satellites, because the magnitude limit is much fainter, 26 or something. And this is also shown the some planned magnitude limit of LSST. So LSST is fainter, so LSST can discover more satellites probably. Okay. So based on this motivation, we are now working on the systematic survey of search for new Milky Way satellites based on the so-called HSC Super Strategic Program, in short HSSP. And this is a very it's a special program and allocated to Japanese super community, and as well as some collaboration international partners of HSC. We have 300 nights over 5 years, and this program consists of 3 layers: wide, deep, and ultra deep layers. Wide, it's along the equatorial area, and deep is somewhere here. Okay. So original goal is to survey over 1,400 square degree, but the survey have been delayed or canceled sometimes due to weather, bad weather or something. So actual final goal is 1,100 square degree. So I'd like to show now as our current result based on the data taken until 2018. I mean the 680 square degree. And these results are already published in these papers. Okay, so using HSC-SSP data, first to to derive the new satellites, we need separate distinguish point sources from the galaxies. Galaxies have extended image. So we first select the point sources from the this photometric data, and it's a parameter as extendedness. And then but still distant galaxies show point sources, have point images. So to remove such contamination and separate between stars and galaxies, we adopt the color diagram, G minus R versus R minus I, and galaxies are red and stars are blue, and stars along the show some narrow band. This is the main sequence, and this is a very red M12 stars. So, and there are some contamination, such as quasars or something else. So we select this region as a target halo stars. And then, from the HSC photometric imaging data, we select point sources and separate likely stars. And then our interest is to find some overdensity of stars, I mean the satellites. So we try to find such overdensity of stars through isochrone filters, because satellites has their own chronological diagram distribution for stars. So stars in the each satellites should distributed in the chronological diagram in a systematic way. So so this is isochrone filter, G minus R versus R. So member stars in each satellite should distribute in this band. This main sequence, subgiant, and red giant branch, and horizontal branch. So we set this isochrone filter as a function of the age and the metallicity. And so with this filter, we pick up the stars and then try to find some spatial overdensities with sufficiently high statistical significance. So in this way, this is the method, but it's complicated. Need patience, and this work was led by my former student, Daisuke Homma. This guy, he already left our department, and he's now working at a private company in the for the space software. So anyway, so based on this method, we discovered first a new dwarf spheroidal galaxy in the direction of the Virgo, and since it's the first satellite discovered in the concentration of Virgo, the name is the satellite is as Virgo 1, and this is a discovery Karl-Marx diagram, and as you see, these black dots is the stars distributed in a systematic way following this isochrone, and And density distribution look like this. And here is red is the dense part. And we also plot the magnitude diagram for stars outside this region. And we found that stars outside this region are random, not follow this one. So in this way, we found this bug one. And and similarly, we found more dual satellites. Okay, so this is a first paper. And after that, we revised our method, and the parameter is somewhat revised. But anyway, this bug one has a V1 absolute magnitude of only minus 0.33. So it's very faint. This total brightness is sum of the stars inside this blue band. So this galaxy, it's so-called ultra-faint dwarf galaxy, consists of just only a few number of red giant branch stars and faint main sequence stars. So this very diffuse, and so that total V1 absolute magnitude is very faint. And so, yes, and so far it's probably the faintest satellites or faintest, say, galaxy in the universe discovered so far. And it's at distance of 90 kiloparsec from the sun. And RH means the half-light radius. It's only 47 parsec. Okay, it's small. Next, we discovered this one in Cetus. So our name is Cetus 3. It's the third those satellites. And again, these stars follow this isochron. And it's very distant. It's 250 kiloparsec from the sun. So it's located at the outer part of the halo. And half-life radius is again around a few tens parsec. Third one is Buddhist 4. It's bright because there are many stars inside this isochron. And V1 absolute magnitude is minus 4.5. And again, this is located at very distant domain in the halo, 200 kiloparsec from the sun. And this half-life radius is large, 460 parsec. Okay, so these are newly discovered satellites. And we also discovered this very compact stellar system. And as you see, these basically comprise of the many main sequence stars, and the only few RGB stars, red giant branch stars. And this is so compact. And so a half-life radius is only 6 parsec. And since this is most probably a globular cluster, not satellites having some extended spatial distribution, so we put this name as HSC1 because this is possibly the first globular cluster discovered from HSC data. So we put the name HSC1. So in the case of globular cluster, sometimes we put name with survey, the camera or survey name. But in the case of satellites, we use the name of the constellation. Okay, this is a diagram for our discovered satellites, and also the Milky Way dwarf satellites known so far, shown as field squares, and Milky Way globular clusters, dot. And x-axis is a half-light radius in units of parsec, RH, and y-axis is V1 absolute magnitude. Okay, this one. And as you see, the red star are newly discovered satellites, and this dotted line is a constant surface brightness. And so newly discovered satellites are very faint. V1 surface brightness is of the order of 32. And so it's fainter than other Milky Way spiral galaxies. And as you see, these dwarf satellites have a systematically larger half-light radius than those of globular clusters shown here. So although globular clusters have a similar brightness, the size is different. So in this way, we can distinguish between the globular cluster and the lower spiral galaxies. And since the half-life radii of the newly discovered satellites here are larger than globular clusters, apparently, so these we conclude that these are satellites, not globular clusters. But HSC-1 is located here, and it's a bit subtle. Size is in between globular cluster and also the galaxies. But we think this is one of the globular clusters, but we need really follow-up observation studies, say spectroscopic follow-up studies are needed to make a final decision. Okay, so bottom panel is again the V1 absolute magnitude versus this time the heliocentric distance from the sun in units of kiloparsec. And as you see, the here the red star are our newly discovered satellites. HSC-1 is here, and this line is the limit of SDSS. Magnitude limit is here. So these newly discovered satellites are actually beyond the reach of SDSS. Okay, and this blue line is a HSC limit. So it's VAG1 theta 3 is and HSC-1 as well as on the border. So HSC combined with the Subaru and this strategic program is very powerful to identify very distant stellar system. Yeah. So this region is unexplored region. So we started to discover some new satellite galaxies. Okay. So next. So what is the implication for the missing satellites program? Okay. Here the red region, the region that was handled by the red line is HSC-SSP survey area until 2018, and field squares are non-dwarf spheroidal galaxies, and red star are new DSPHs, say VAG1, Vs.cored, and Theta 3. So in the S18A is a survey until 2018. This footprint, actually there are 6 dwarf spheroidal galaxies. Okay, 3 are already known: Sextans, Leo 4, and Pegasus 3, and 3 new dwarf spheroidal galaxies. log1 multiple and zeta3. So this red region, say a 680 square degree, there are 6 dwarf spheroidal galaxies. Okay, so based on this number, and so we would like to get some insight into the missing satellite problem. So we like to compare with the theoretical models. Theory, okay, theory is based on the dark matter model, and the dark model predicts some number distribution as a function of the mass of the subhalo and the position of the subhalo within the host halo. Okay, and point is how to transform this information to the visible satellite properties. Say total number of the satellites as a function of the brightness of the satellites, V1 absolute magnitude, and position of the satellites. Yeah, so this part is a bit complicated. But I like to, I'm going to try. I try to explain. This a bit complicated. Okay, so this is one example. Newton et al. 2018. They investigate the radial distribution of the dark matter subhalos in the simulation, and compare with the total number of the satellites discovered with strong, and this is a dark energy survey. Okay, and okay, so the basic assumption is that number distribution of the satellites within the host halo Milky Way galaxy follows a centrally concentrated inust profile. It's a Cuspy profile, as I explained in lecture 1. And since the Sloan and the dark energy survey observe only some limited sky area, so this, and also there are some limitation in the direction of the line of sight. So survey volume is limited. So we need to make a completeness corrected. So theory predicts some distribution of satellites within the host halo, but we observe only a limited volume, given the limiting magnitude and survey area. So this is so-called completeness corrected. So okay, so combined with the centrally concentrated inust profile assumption with the total number of the galaxy satellite discovered with strong and dark energy survey, they arrive at the total number of satellites 124 at V1 absolute brighter than 0. Okay, this is a prediction. Okay, so again, I repeat that the total number of satellites predict is 124. And of course, this is total number of the subhalo is hundreds, much more, as I explained. But since there are some baryonic effect or some non-reinteraction and some subhalos are disrupted, or star formation suppressed in some subhalos. So after that, probably the total number of satellites is reduced, and so this complicated baryonic effect is omitted by comparing the actual discovered number of the satellites so far and some assumption on the distribution of the satellites. Okay, so it's a bit complicated, sorry. So if we adopt this theoretical prediction and apply to our survey, the predict number of the satellites following this number is 2 in our HSC-SSP footprints. But as I already mentioned in the last page, there are 6 dwarf solitary galaxies in our footprint. So observation predict more satellites. So say it's a kind of too many satellites problem instead of a missing satellite problem. Okay. So this is show the status in comparison with the Newton-Eton model. Okay, this is a V-band absolute magnitude and cumulative number of the satellites. And this black line is all satellites from theoretical model. And as I said, the total number of the satellites is 124 here. But we observe only a limited sky area, say 680 square degree. So correction is made for this sky coverage and this blue line. So number is here. And also the we observe only a small volume. I mean the line, the limiting magnitude is set. So there are some also correction, and the combined correction is shown in the red line. And so if this correction is made and follow the Newton-Eton model, extreme number of the satellites is around 2, but actually observed number of the satellites is 6. So we observe more satellites. Okay. So too many satellite program. So based on the lambda CDM. But it is inconsistent with warm dark matter model prediction. Warm dark matter prediction is somewhere red, so or more less. So I omit the detail. But anyway, this is the state, the current situation. And there are several other theoretical models. Okay, next one is the Doolittle model, 2017. This is a more simplified model. They they conducted the dark matter only simulation and abundance matching. This means the transformation of the dark matter halo, mass of the dark matter halo to the even absolute magnitude of the satellites. This is so-called abundance matching. And the more important point is that they assume less centrally concentrated distribution of satellites than the I-1 NFW profile. And they arrive at total number of satellites about 1,000. And if we adopt their model, then we obtain this number for our HSC-SSP footprints, 6 to 12 satellites. So this is compared to observed number of satellites 6, it's not so bad. Okay. So there's some uncertainties depending on the theoretical models. So what's the matter in the theoretical models? As I said, okay, theory predicts the total number of the satellites in some volume, and we need to compare with actually observed local volume. And so we need a complete is collected. But the key is the assumption on the radial distribution of satellites. And this shows some cases, the radial distribution of satellites as a function of the distance from the main halo, Milky Way halo, and the y-axis, the cumulative number of the satellites. And the NFW essays, and this is centrally concentrated density number distribution of the satellites. In this case, the theory predicts about 124 100 satellites. But if this less centrally concentrated distribution satellite is assumed, then the theory predicts a total number of satellites of the 1,000. And so far, the theoretical model adopts satellites rather near the sun. So this part of the satellite, this part of the sun, this part of the space. So there are some uncertainties. So to pin down this one, so whether the central distribution satellites here or here, you really need information on the distribution of the satellites in the outer, more distant domain of the halo. And this is very difficult part because upper molecule satellite will be faint. So we really need big telescope like Subaru and other telescope. So anyway, so there are some uncertainties depending on the radar assumption on the radar distribution satellites. I hope you understand this. Sorry, it's a complicated part. And more complicatedly, this is the latest theoretical studies using latest information on the discovery of satellites using the dark energy survey or PS1, the Pan-STARRS one, combined with the cold model-based galaxy formation simulation. And these people, consider galaxy formation efficiency factor as a function of the mass of the dark matter halo, subhalo. And this is abundance matching, as I said, matching between the mass of the subhalo and brightness of the satellites. Then one can obtain such a luminosity function of the satellites. And this paper suggests this total number. It's 220 satellites in the VQM. So if it's true, it's a double of the Newton et al. So Newton et al. Suggests 124. Yeah. So, but this work also does not consider actual number distribution of the satellites in the outer part of the halo. So there's still uncertainty. So okay, sorry, it's a complicated part. So anyway, what is the implication for the missing satellite problem? Okay, probably the problem is now less serious than previous thought, or problem might be solved. But as I said, we need to refine the relation between subhalo and satellites, including a number of distributions, spatial distribution satellites as a function of the distance from the galactic center. This is very important. And okay, so we are now in the level of refinement between the observational data, because observation discovered many satellites, more and more satellites in comparison with the theoretical models. So one point is made clear that warm dark matter model suggests less number of the satellites, much less than 100. So this model can be ruled out. It's already suggested. But anyway, the key is to understand the true spatial distribution of satellites by obtaining new satellites in the outer part of the halo. So we really need a deep survey, HSC-SSP and LSST, okay, to really set limits on this satellite program. But anyway, how to say, we are now in the stage of refinement for this satellite program. And let me briefly say that we discovered more, actually. We haven't yet published the result. And this new results suggest that spatial distribution satellite is less centrally concentrated than INAS to NFLW profile. So anyway, we like to work more on this based on these new results. Sorry, this part is complicated. And of course, we need spectroscopic follow-up studies to. We just discovered the satellite candidates, but some stars might be field stars. So there are some contamination. So to separate out such a contamination, we really need follow-up studies, spectroscopy. So this work is now ongoing. And for example, Cetus 3, there are only a few number of RGB stars here. So we obtain already some spectra using Keiko Deimos. This work is led by our colleague Miko Shigaki, and his work is now going on. But as you see, many member stars are much fainter than say R of 22nd magnitude. And right now, with the current 8 to 10, 10 meter telescope, so the meter is missing, it is impossible to obtain spectroscopy for such faint stars. So we really need 30 meter telescope, TMT, to follow up the spectroscopic follow-up of these faint stars. So final decision on whether this is really satellite will be made when the TMT is up. Okay, so summary: new Galactic satellites have constantly being discovered, and the discovery state may be understood in the framework of CDM plus capacity formation model. Sorry, it took so long. So let me very quickly show second issue, the core cusp problem. Okay, as I said, some jobs through the galaxies show core central dark matter profile. And this is based on the analysis of the member stars in each of the satellites. And here shows the dispersion profile as a function of the distance from the center of the distance from the center of each dose-order galaxy. So dispersion is of level 10 km per second. And analyzing this line of sight velocity dispersion profile, one can obtain the background dark matter density profile. And as I say, some jobs already have a core-like profile. Okay, let me skip this one. And okay, I'd like to just say that the many models are based on very simple assumption, spherically symmetric mass model. And it is very simple to solve, but there are some degeneracy among the parameters. So we revised this spherically symmetric mass model for those weather galaxies. It's led by my former student, Kohei Hayashi. And apparently, observed observed galaxies are not spherical. Okay, Sculptor, Wilson Minor is not spherical, it's symmetric. It's difficult to recognize, but actual ratio is actually 0.68 and 0.44, yeah. And also the dark matter distribution is also not spherical, as I already said in lecture 1. Basically, the triaxial. Anyway, non-spherical. And data analysis of indexes only a 1D spatial distribution as given the assumption of the under the assumption of the spherical symmetry. So although the spherical symmetry assumption is simple and easy to analyze, but it's far from reality. This shows some the effect originating from the difference between spherical and non-spherical cases. This shows the okay, major axis, minor axis. This shows the contour of the line of sight velocity dispersion of stars based on the spherical symmetric model. So spherical symmetric, so that line of sight velocity dispersion profile is spherically distributed. So it's okay. So one can analyze a 1D spatial distribution of the space, 1D spatial distribution of line of sight velocity dispersion. But actually, when we drop the assumption spherical symmetry, then the contour line of sight dispersion is like this. So it's the global pattern is so different from the case of spherical symmetry. So and also this shows that solid line is the case of cuspy dark matter and dashman the core. So there's some difference. So this 2D distribution of the line of sight velocity dispersion, the stars is so important. So we are working on this non-spherical mass model for the observatory galaxies, and actually we adopt the asymmetric mass model. So yeah, and okay, let me skip the results. Okay, this is dark matter density profile for Draco and Fornax, and this is a result based on the currently available line of sight velocity data. And as you see, the Draco shows kind of a cuspy density profile. And gamma is the index for the slope of the dark matter density profile in the inner part. And Fornax is somewhat mildly cored. Okay, the index is 0.5. Actually, we analyzed the 8 dwarf stellar galaxies, and there's a diversity. And again, I'd like to emphasize that this is based on the currently available radar velocity data, but data is limited right now. But anyway, there's diversity. And so, and Draco is Cuspy, as I said, Ursa Minor as well. And these guys are kind of cored, mildly cored. Okay, so there's a diversity. Okay, why? Why there's a diversity? It's probably due to baryonic feedback effects on dark matter cusp, or central part of the dark matter. This shows the effect of the baryonic feedback based on numerical simulation. And okay, y-axis is the slope of dark matter profile. It's gamma, and gamma around minus 1.5 is cusp, and gamma around minus 0.5 or 0 is a core here. And this gray shaded line is before the feedback, baryonic feedback. And after baryonic feedback, simulation suggests such a systematic change of the slope due to this baryonic effect. So this baryonic effect makes the slope gamma, how to say, cored or smooth out. Cuspy density profile of the dark matter is smooth out due to the baryonic effect. But this effect is smaller for fainter galaxies. X-axis is stellar mass divided by dark halo mass. Okay, and this is the ultra faint dwarf galaxy domain. Classical dwarf is a slightly bright dwarfs, and the bright dwarfs is here. Okay. So information scale dwarf scale is essential in, to set limits on this physical process. So we put our analysis result here. Okay, so as you see, there's still some dispersion or diversity, and each satellite has a large observational error. But there's some, as you see, the trend like this. But honestly, it's not conclusive. It's yet inconclusive. So we might adopt the alternative dark matter model. So for example, in the case of self-interacting dark matter, HSC-SSP, all the dark matter is cored. So this one is moved up. So it is yet uncertain. And the main reason is that available number of radiability data is quite limited for each of these dwarf-threaded galaxies. Okay, there are several dark matter candidates, as I mentioned, and core dark matter. This is the mass scale of dark matter. Core dark matter is somewhere here. But there are several other candidates recently discussing very seriously. This is based on the review by Elisa Feria. So there are several other candidates, including primordial black hole in the scale of the 10 solar mass, ultra-light dark matter 10 to the minus 22nd electron volt. Okay. So if we adopt this ultralight dark matter, then the dark matter profile looks like this. Here shows the theoretical prediction when we adopt the ultralight action dark matter, and in this case, the mass of the each particle is of level 10 to the minus 22nd electron volt. It's very light compared to WIMP. And if we assume this one, then the dark matter density profile is show this large core in the inner part. This case is not yet rejected because, as I said, currently available observational data for line of velocity is still very limited. So this is based on the currently available data, but we think that this trend might be modified. This way, in which way, we don't know yet. So we really need more data. So lastly, I'd like to show future prospects on this issue. Okay, we are now in the Subaru. There's now much object spectrum is now prepared. It's a so-called prime focus spectrum attached to prime focus. It's in short, it's so-called PFS. And this PFS has a large diameter, 1.3 degree diameter in diameter, and it has many fiber positioners. Say 2,400 fiber positioners. Means that this spectrograph can get this number of the spectra at the same time. And this is 3 channel, blue, red, infrared. And so scientific run is scheduled from 2023. And this is based on the international collaboration led by Japanese university and Subaru, plus other institutes, Caltech, Princeton, JHU, and other, including Taiwan and Chinese consortium as well. And so PFS is very powerful for the studies of the dark matter profile or nature of dark matter in the scale of dwarf-threaded galaxies. This is one example. This is for next of solar galaxy, and this dotted line is the nominal tidal radius. It's a bit large. And this inner region, this small circle, this is shows the previous range of measuring the dark halo profile. I mean, the radio bliss is available only in the inner part of the fornax. And detailed abundance ratio studies available possible only in its innermost region, and radio bliss measurements are made only here. But galaxies this has a much larger radii, so it is not we really need more data for radiability. But PFS is, as I said, a large aperture, 1.3 degree in diameter, and it has a lot of 5 positioners. So only 4 pointings, we can cover basically all the part of the fornax and obtain many spectra of the stars at the same time. So with this machine, we like to map out the dark matter of the fornax, and we like to set limits on the nature of dark matter. This is a list of the PFS targets for those cellular galaxies, and each those cellular galaxy we put only a few pointings. Only a few PFS pointings is enough to cover the whole area of the each of the those cellular galaxies. And so we like to put limits on this. Okay, and these galaxies. Okay, sorry. Some of these, so we can put limits on whether the real galaxy, really this trend is like this, or following the, or all galaxies might be core. We don't know. So yeah, PFS will give us the right answer. Okay, this is sorry, last slide. Concerning, there are several still unsolved issues, of course, in the dark matter in the scale of Milky Way. So during next decade, there are a lot of facilities to be used for the for these issues, such as Subaru, as I say, HSC, PFS, and others. And ALMA provides us high-resolution observation of gravitational lensing, which can set limits on the dark nature of dark matter in small scale. Gaia, this provides the dynamics of the stars. And then we also will also have TMT, probably around 2030, and it provides a spectra of many ancient stars, and so it's very important. So with these facilities, we hope to understand the nature of dark matter, hopefully within 10 years or something. So it's already okay, 17. Okay, sorry. Okay, that's it. I'm wondering, this lecture 2 is a bit complicated, but I hope you understand main parts of this lecture. Okay, thank you for listening.
Yeah, thank you very much, Professor Chiba. Now it's time for questions. We have already about 1 to about 3 questions.
Okay,
First,
yeah.
from Thomas Nabil, please.
Yes, I'm
Yes,
here.
please.
Thank you, Professor, for the lecture. I wanted to ask, are alternatives to cold dark matter, such as the W dark matter or SIDM, able to explain the large-scale structures such as cold dark matter or not?
Okay, this theory also predict similar prediction to that of the lambda CDM. I mean, SIDM, WDM predict basically the same light scale structure because, for example, warm dark matter has same power spectrum. So in the large scale structure, WDM predict basically the same large scale structure as that of CDM. So difference only in the small scale. Okay.
So these alternatives are considered to be refinements to the cold dark matter. Can we consider
not refinement?
this?
Not refinement. That's basically the different dark matter model.
Okay.
Not refinement.
Thank you. Yeah. Thank you, Doctor.
Okay, thank you, Nabil. The second questions from Sharif Faris. I will read it. How optimistic do you feel that better surface will solve the missing satellites problem? And what alternatives models will be more favored if more and better surface simply can solve the problem? Yeah, that's
yeah.
Thank you.
Thank you. So is a quick question or
yes, the question is about alternative. How optimistic do you feel that better surface will solve the missing satellite problem? That's the first questions.
So I'm basically optimistic to this is we are now in the stage of kind of a refinement, as I mentioned, and theory are still a lot of uncertainties, and we are still observational data is still very limited. For example, HSC observe only a small scale area. So I think the LSST, I think the current name is Belarubin Observatory, and I forgot the name, but the LSST is survey a very large area in the sky. So LSST will finally put maybe final answer.
Okay, and the next question from Sim Sharif Faris. And what alternatives models will be more favored if more and better surface simply cannot solve the problem? Yeah. Alternative models.
Alternative dark matter model, you mean?
I think so. Yes.
Yeah. Well, to be honest, now it's concerning dark matter candidate. It's chaos. As you see, so many candidates right now because wind particle are not yet detected from experiment. So and there's some tension, as I mentioned. So people are now considering many alternative models. So but for instance, as I said, cusp problem, the ultralight dark matter model suggests core profile, and SIDM, it's not included here, is also predict core profile. So based on the PFS observation of the Milky Way satellites, then we can, I think, distinguish finally some dark matter model. So in this way, we can narrow down the likely window of the dark matter candidates along this axis. Okay, more observation are needed to set limits on this window of this dark matter candidates. So right now I don't have a quite free answer. Sorry.
Yeah. Okay. Thank you for the next questions from Arif Nurrahman. Please, Arif.
Okay.
Yeah.
My question is, can dark matter made of from black hole? So what is the first axis in the universe, observational universe, black hole or dark matter? Because in your slide is one of the candidate of dark matter is primordial black hole.
Yeah, yeah.
Sorry, my question is not so good. Thank you, sir.
Well, there's still possibility that the dark matter made of primordial black holes. Primordial black holes are formed in the early stage of the universe, and the mass scale is of the Earth mass, Moon mass to 10 to the solar mass or something. Yeah, there's some spectra, and there are some constraint on the abundance of primordial black holes based on the microlensing technique. If the dark matter halo of the Milky Way or Andromeda Galaxy halo is made of primordial black hole, then this yields the microlensing phenomena. We actually put limits on some window of the primordial black hole the axis based on the HSC observation and in the direction of the Andromeda Galaxy. And we set limits, we narrowed some windows for black hole, in the case of primordial black holes. But anyway, still there is possibility that the dark matter is made of the primordial black hole. So, and the microlensing technique is very efficient to rule out or to accept maybe to that candidates that primordial black holes in the dark matter here. Is it okay?
Yeah, Arif,
Yeah.
can you can also ask the second questions? Your second
Yes.
questions, okay?
What is first axis in the observable universe? Black holes or dark matter? The first axis in the observational universe. First axis.
First axis. Sorry,
First appearance, I think. First appearance. Dark matter or black holes?
First appearance.
Yes, I think.
It's how to say first appearance. Okay, first appearance. Well, universe is basically okay. In the early universe, it's there's some fluctuation in the mass, and this fluctuation is resulting in the maybe primordial black hole or other dark matter halos. So if primordial black holes really exist, then it's probably the first collapsed object in the universe. Yeah. So primordial black holes be first appeared, then the dark matter halos appeared. I understand. I think.
You.
Okay.
Thank you, sir.
Thank you. Next is Muhammad Rafif Rabani, please.
Okay. Hello, sir.
Hello.
I'd like to ask. You mentioned that one possible cause for the variation in the density profile, whether something could be cuspy or chord, is baryonic effect. Now,
Yes, yes.
I would like to, would you please explain to us what sort of processes are happening in those?
Sorry. Baryonic feedback is driven by supernova explosion. It's and the resulting heating of gas. So suppose dark matter and the gas and star formation occurred, and right after that the supernova explosion happens. Then the gas is brought away from the bottom of the dark matter halo, and since mass is lost, dark matter profile is smoothed out due to the loss of the gas. So density profile is somewhat smoothed out like this. So this is driven by supernova explosion and loss of the gas in the central part of the dark matter halo. But in the faint part, amount of gas is so small, so that the effect of this feedback is very small. Okay, and this part is mass of the gases baryon is large, so that due to a large amount of baryon or gas or stars in the central part of the dark matter halo, it's baryon or gas or stars also attract dark matter particles, so that there's a so-called adaptive collapse happens here. So slope is steepened. So anyway, this part is driven by supernova explosion. Sorry, I didn't explain this page. Okay.
Okay. Okay. Thank you. Now the next questions from Bu Premana. Please, you can.
Hi, Chiba-san. Thank you for
Hi.
the very nice explanation. I was just wondering, you know, I don't have much chance to see you, so I just slipped my question in. Would you comment on bar structure, please? Would that have any relation at all with the cusp core issue?
What relation?
It's a bar structure.
A bar structure. Yeah. Yeah, bar structure can you know, the interaction between bar structure and cuspy dark matter.
Right.
Change the probably profile of the dark matter there, and this kind of effect is probably included naturally in this simulation, because the bar formation sometimes occurs in the galaxy formation simulation. So it is difficult to separate that which one is the bar effect here, but everything is included in this diagram. But as you suggested, bar is important to change the dark matter density profile.
Thank you.
Okay, thank you, Bu Premana. Next questions from Dr. Hla Miatandar. Please.
Hello, Professor. My question.
Yes.
My question is, why does dark matter form a halo?
Sorry.
Why does
why
dark matter form?
why the dark matter forms the halo?
Yes.
Yes.
Okay. Because dark matter particles basically it's collisionless, no dissipation. So once this dissipation is a kind of star, no radiative cooling. So it's just particle and no collision. So if such a collisionless particle collapse, then the how to say each particle has a random motion of the 200 kilometer per second, and since there is no dissipation, no loss of kinetic energy, binding energy, so these particles are distributed over the large spatial area.
Thank you, sir.
Mm.
Thank you, Prof.
Okay, thank you. Now there's last questions from Murulani. Please.
Hello, sir.
Hello?
Yes.
I have two questions. One
Uh-huh.
is there any relation between the sun being a single star rather than being one among a cluster and the position of the Sagittarius stream passing through the disk of our Milky Way galaxy, which is close to the current position of the sun, or any other merging with the dwarf galaxy could account for sun being a single star? And the other one, would any of these collisions could account for the feasibility to originate life in the solar system, or could anything point to the exact source of water here?
So I'm sorry, it's
First questions
you,
first, Murulani. Can you
say
repeat?
you say a bit bit fast, so it's
I asked,
yeah.
any star
Very quick.
will be
Could you
found-
say brief, very short and slowly? Okay, sorry.
Stars form in groups,
Yes.
not as a single star, but our
Yeah.
sun is a single star.
Mm-hmm.
So is any of the collision or this Sagittarius dwarf galaxy being stripped into stream could account for the sun being a single star and not as a multiple star or a part of a cluster?
That's a interesting but difficult
There is
question.
no relation.
No
Yes,
relation. Yeah. It's a no relation because Sagittarius, the stars in Sagittarius galaxy's stream is more metal poor than the metallicity of the sun. So from this observation evidence, and also the motion of the stream is different from the motion of the sun. So so from the chemical abundance information and orbital information, it is difficult to put some link between the sun and the stream. Is it okay?
Yeah. If there is no interaction could happen,
no
then
interaction.
Yeah.
Okay. So what is the second question?
Yeah. Only if the first is answerable, then the second valid.
Okay.
Okay. Yeah. Thank you, sir. Fine.
Thank you. Yeah.
Yeah. Thank you. Maybe one questions more from this morning. Dafa Wardana, please.
Oh, Dafa.
Yes.
Hello.
Dafa,
how are you?
Please.
Hello.
Oh, hello. How are you? Sorry. So it's you right now you cannot come to Japan.
Yes, it's no problem. You can just talk
Okay.
online.
So-
Thank you, Mr. Iqbal, for the question, and thank you, Chiba Sensei, for the presentation. I want to ask about material from the previous lecture, actually, about the lens flux ratio.
Okay.
Is it possible for the lens flux ratio for a certain object to have different value if we observe in several different wavelengths? And if it's possible, will it give anomaly in a certain wavelength, but no anomaly detected in another wavelength?
Yeah, you are correct. Yeah, it's a very important question. What I show in the lecture one, in the case of PG, something is it's based on the rather short wavelength observation, and but in that case, there are some uncertainties in as a origin of the anomalous flux ratio. As I mentioned, it might be due to microlensing by member stars. But to distinguish between such microlensing and lensing perturbation by subhalos, we need observation at longer wavelength, because there's some difference in the Einstein size of the Einstein radius between microlensing and lensing by subhalos. So so it's difficult to answer this in the very within the short time, but longer wavelength observation is essential to distinguish between the this microlensing case and lensing by subhalos. So for detail, please take a look at my paper published 2005. Sorry. We made several observation with a mid-infrared observation for that lensing system showing anomalous flux ratio, and we put limits on the origin of the anomalous flux ratio, whether this one is by microlensing or this one is by dark matter lensing. So, okay. So,
okay. Thank you very much for the answer.
Okay, thank you very much for all the questions today, and also we thank you, Professor Masashi Chiba, for this very nice lectures. Now we'll stop here, and at the end there will be photo sessions for the second one. Please, Okta. Yeah.
Okay, wait. Let me see the first. Okay, first slide. Second, wait. Okay, that's all. Thank you.
Thank you.
Thank you very much.
Thank you
all
very much,
participants
Professor
and
Chiba.
Professor Chiba.
Thank you.
Thank you,
Thank
Professor.
you
very much, Mr. Professor.
Very much.
Okay, thank you for listening, and see you.
Thank you very much.
Thanks,
Thank you.
Chiba Sensei.
Thank you very much.
Bye bye. Okay, I leave.